Cisco High Density AP Deployment Enterprise Design Recommendations. So Wi-Fi 6 is here. What's changing? Well, conversations we're having. We're talking about 8K video. That's 80 megabits per second per client conservatively. Augmented reality, virtual reality. Lots of applications coming down the pike that give us amazing capabilities we've never known before. So the question then gets asked, does a generalized guideline of 1 AP for 2,500 square feet, which has served us well, been safe in almost any regulatory, does it still serve the need for these kind of capacities? To find out, we went out to Richfield, Ohio, where we've got a 15,000 square foot lab. Gives us the opportunity to test open office, cubes, walled offices, and we put together a couple of configurations at 20, 40, and 80 megahertz. And then we did that at three densities at 1,000 square foot per AP, 1,200 square foot per AP, and 1,500 square foot per AP. The goal of this was to evaluate the channel plan and the usability of these networks. We used Ekahau Pro and a Sidekick to evaluate the ground truth. We also used Ixia Chariot for the performance results. Why? Higher performance inside of a cell requires more cells to serve all the users. AP isolation is the key thing we're trying to beat. Wi-Fi operates on a contention mechanism, so two APs on the same channel that can hear one another are going to share the channel. That's by design. If three APs can hear one another at the same distance, they're all going to get a third of the channel. So if you have more channels than APs, all's going to be isolated and you have no worries. Channel bonding makes a difference. A 40 megahertz channel is two 20 megahertz channels, and an 80 megahertz channel is four 20 megahertz channels. Keep in mind, dual 5 gigahertz requires 2 times the channels per AP. APs shouldn't be closer or be able to hear one another on the same channel above minus 82 dBm. That's per the 802.11a specification. Does that mean that if two APs can hear one another at minus 82 dBm that they're instantly going to get half the bandwidth? No. But the closer they get to one another, the more impact is going to be felt. The other thing that factors into the equation is channels. Around the world, channels are not the same number in all regions. In the US, we've got 25 20 megahertz channels. In Europe, you only have 19. In India, you get 16. And depending on which regulatory you're in, you could have less than that. So we start by evaluating 1,000 square foot cells at 80 megahertz channel. 5 gigahertz interfaces, we're going to have 15 APs and 15,000 square feet. At 80 megahertz, we have 6 channels in the US. So the equation then is 15 APs divided by 6 channels, and it's going to give us a reuse of 2.5 times of the channel plan. 10 of the 15 APs are going to wind up on duplicate channels. How that measured out, you can see at the right. We're showing just channels 52 and channel 140. One had 3 APs on it, the other had 2 APs on it. Co-channel neighbors for all 10 APs were seen by each other at or above minus 65 dBm, so they were very well coupled. The results that we're showing were at the lowest power level, which is where the power plan wound up with that many APs on that few channels. Co-channel interference in this case would be very high. Performance issues would be noted. It would be uneven response throughout the facility. But what if we back that up to 40 megahertz channels? Well, that effectively doubles the number of channels that we have to work with. It also puts us at a channel plan reuse rate of 1.25 times and leaves us with only 3 APs that are in co-channel pairs, so 6 APs instead of 10 APs. We found 3 co-channel pairs. The distance in RF between these pairs was minus 70 dBm for the best, minus 64 dBm, and minus 54 dBm for the closest. All of these values are above the minus 78 required for isolation. But to evaluate this, we decided to pick a co-channel pair and test both simultaneously. For that test, we chose the minus 64 dBm pair. It wasn't the worst, it wasn't the best, and we loaded each AP up with 8 clients. Now for reference, a single 40 megahertz AP operating without contention, 8 clients for 8K video client streams, we saw a throughput of 760 megabits per second, or 90 megabits per second for each client. One-way latency was below 50 milliseconds, which is excellent. When we loaded up our Cochannel pair, that throughput for 16 clients on 2 APs dropped to 535 megabits per second, or 33 megabits per second per client on average. Latency quadrupled. That cost us 220 milliseconds one way. That's unacceptable for round-trip voice and video. Individual client experience also ranged from 20 megabits per second to 60 megabits per second and was not stable throughout the test. So the quality of experience suffers. Keeping in mind, this is 2 fully loaded APs. If these APs were half loaded, they'd probably be very acceptable results and you may not even notice. But if you're looking for critical applications, they're going to have to be isolated, and you would notice in this case. If we back this up again to 20 megahertz channels, we've got more channels than we have APs. We don't have any contention problems, and we get full throughput. How many 8K clients can we get on a single AP at 20 megahertz? Well, we tried it with 4. And we got 346 megabits per second, or 86.6 megabits per second per client. So what happens if we reduce the number of APs? If we move out to 1,200 square foot cells, then the channel plan only requires 12 APs at 5 gigahertz. And at 40 megahertz channels, we have 12. So in the US, we never repeat or reuse a channel. We have no contention issues. We'd expect excellent performance, single cell performance across the entire facility. But we wanted to push it a little further. We removed some channels, we forced some co-channel interference scenarios, and we got some duplicate channels. But even here at 1,200 square feet, we had enough room so that the closest one was below minus 78. dBm, and we could have easily tuned this out and wouldn't have expected to see any performance impact, regardless of how many of these cells were used at once. If we back that up again to 15,000 square feet per AP, we're down to 10. We again don't reuse channels, and this is probably supportable in just about any regulatory on the globe. So what did we learn? At 1,000 square foot per AP, 80 megahertz is probably not supportable in the US or anywhere else. 40 megahertz, on the other hand, has some caveats. It can be supported, but it's going to be at some cost. And if you happen to load up multiple cells that are co-channel pairs at the same time, you will see less performance. And you should expect to see some reuse of channels. Again, most applications, not going to experience a problem with this. If you're 1,200 square foot per cell in the US and in Etsy, 40 megahertz is very supportable. And at 1,500 square foot per cell, you're supportable anywhere in the world. I hope this information was useful. Keep in mind your mileage will vary. Not all offices are built the same. Get a good plan and have a good time. Take care.